This is Navin Joshi. I am from Department of Physics, SRM University, Delhi NCR. And today I'm going to talk something about one of my research paper that I've recently published. And the title of my talk is Evolutionary Stages and Triggering Processes of a Complex Eruptive Flare with Circular and Parallel Events. So basically it is more about the flare events that occurs in the solar atmosphere. So these are my collaborators, Dr. Bhuvan Joshi and Pravir K. Mitra from Udaipur Solar Observatory for this work. Okay, so I will start the introduction about the solar flares. So here in this picture, you can see one of the background image, that is the image of the sun in 131 angstrom. And it in the figure, you can see some chunk of brightening in some localization. Basically, in the southern part of the sun, that chunk of brightness, this kind of brightness on the sun's surface is usually called solar flares. So these are basically nothing but the release of magnetic energy in the sun, and the release of magnetic energy usually occurs by the process of called magnetic reconnection. Okay, so you for the more detail about the flaring event and reconnection, you can go through these review articles by Benj and Shibata. So here in the plot, you can see in the x-axis you have universal time, and the y-axis you have watt per meter square. Actually, this is the X-ray flux that was recorded by the Goose spacecraft, and it is in the X-ray wavelength. So you can see there are some peaks is occurring at the certain interval of time for some duration. You can see several chunk of peaks here, and these kind of peaks usually occurs in when there is a solar flare occurs on the solar surface. So if you match the timing of this event is here. It is occurred on around 11 UT, 12 UT on 6th of September. So if you go here, so you have two peaks, and these two peaks are corresponding to the flare, two different flare occurring on this region. So that is the difference between the X flares that occurs on the solar surface, that is the observational point of view, and the second is the flux point of view, when you record the flux of the whole sun, and you will see these kind of chunk of brightnesses. Okay, so the important thing when these kind of flares occurs, the first stage is the magnetic reconnection. Second point is the formation of flaring ribbons. Okay, so reconnection occurs in the higher in the corona, which is the outermost means the outer layer of the sun, and the flare ribbon, which is the secondary process you can see is say, and the flare ribbons occurs in the chromospheric region, that is in the higher atmosphere, in the lower atmosphere of the sun, relatively lower atmosphere of the sun. So these are some of the introduction point about the solar flare. This is basically nothing but the release of magnetic energy from some localized region of the sun. And the first stage is a magnetic reconnection. Second is the formation of flare ribbons. Fine. So now I will discuss something about the flare models. So here in this model, you can, this is the one of the best model that we have. It's called standard model of the solar flare. And you can, here in this figure, you can see what will happen is we have, this is a cartoon schematic representation given by the Shibata Kane in 1999. And in the bottom one is the Moore et al. 2001. So basically Moore et al. 2001 is the extended version of the Shibata's model. So in that case, what usually happens is if you have a flux rope and associated with the filament, and if that flux rope erupts, then we have the magnetic reconnection beneath the flux rope, and this is the first stage. And the second, the particles or the free electrons, mainly they channels down to the lower atmosphere of the sun, that is a chromosphere, And in the chromosphere, we will get the flaring ribbons. So here these two circular structure is there representing the flare ribbons. The upper part is the 2D representation of the figure, whole picture. But in the bottom figure, if you'll see, we have the three set of flaring ribbons. So ribbons are basically the elongated structures. So they are long structure, not like just point sources. So actually in the bottom figure, you can see the three-dimensional picture of the upper figure. So here the reconnection region is here, and the two long structures are called the flare ribbon. In the observational point of view, you can see in the middle of the this page, you can see the two bright parallel ribbon-like structures. These are the observational evidence of the flaring ribbons. So basically the parallel flare ribbons. Okay, so this is the image observed by the BBS. So it's a BBS solar observatory. Is located in the US. So finally, this is all about the parallel ribbon flare. So later on, there is a development in the TRACE, the spacecraft. They observed some circular kind of structure in the solar the solar chromosphere or the lower solar heights. They and as well as later on in the H alpha or as well as in the SD observation, we observed some sort of circular kind of pattern after the flare reconnection. Right. In the previous slide, I've told you about the parallel flare ribbons, but here the flare ribbons are not parallel, but these are circular. So of course, the magnetic configuration will be quite different in that case. So if you'll go in the next slide. So here, after some papers, the Sun et al. 2015 and some other guys work on that, and they found that the magnetic configuration for such type of flare occurs should be something like this. So in that case, we will have a dome kind of structure. In the center, we have a one polarity region, which is N1 is the negative polarity, means the negative polarity of the Sun magnetic field, surrounded by the positive polarity region, and then there is a far away negative polarity. So in that case, the magnetic field lines start from the negative, they came to the magnetic null and then went off and connect to the far away negative polarity. So in that case, we will have a dome structure and then some lines going away. So that kind of structure is usually called the fan dome magnetic structure. And the magnetic flux rope usually lie inside the magnetic dome. So here that purple lines are shown representing the magnetic flux rope. So there should be a null point at the top. If you'll see the cross section of the panel A, so in the C panel, you can see how different set of field lines we will have. So in that case, when this flux rope is moving up, okay, so the field line, which is represented by the blue lines, is going towards the null point, and it is reconnected with the blue line that is on the other side. So in that case, we will have a reconnection at the null point, and then the electron will move downwards from all around the dome, and they will form a circular kind of structure. So we will have a dome-like structure, right? So if you'll cut the onion in the half and put it on the table, so that is the dome, right? So that kind of structure we'll have. Okay, so in this continuation, myself started working on such kind of circular ribbon flare events. Okay, so the first work that I published in 2015, in which we found a very large scale circular ribbon structure. Probably this is the first time we have studied or interpret or discuss something about a very large scale structure. And the one more important point is in the previous studies, the people either talked about either the parallel flare ribbon or the circular ribbon flare. Okay, so in our case, we have come because of the importance or because of the importance of the large scale, we have found the combination of both kind of flare ribbon in that case. So in this picture, you can see we have a large scale circular kind of structure, and also in one side we will have a parallel flare ribbons. Okay, so in that case it means there's a combination of both kind of flare ribbons. So we have uh, uh, both the different kind of configuration are there, and it is also satisfying the models that predicts the parallel flare ribbons, and as well as the model that will predict the circular flare ribbons. There's another paper that we published in the same line on 2017. There we have also found the parallel as well as the large scale circular ribbon. Okay, so in both the cases, we have found initially there is a development of parallel flare ribbons, and later on, the parallel flare ribbon is extended and forms a large scale circular ribbon on the solar surface. So these kind of flare, we say that the flare with parallel and circular ribbon flare. So they contains both kind of flare ribbons. Ribbons are the secondary process, as I told you before. At first, we have reconnection, and the second, we have the formation of parallel ribbons or the circular ribbons on the lower solar atmosphere. Now, after that, what was our motivation for the next study was to understand the role of erupting flux rope, because flux rope, which is lying inside the fan dome structure, is very important in that case. So our aim is to understand the role of what is the role of these kind of magnetic flux rope in triggering these kind of flare ribbons or the flares with parallel and circular ribbons. Second is to understand the formation and dynamics of the parallel and circular ribbon, how they will form, what kind of magnetic configuration is there, what kind of reconnection process is there. And the third is the interaction between the different sort of magnetic structure, that is flux rope and the ambient magnetic field. So to explore all these conditions, we have started working on M8.7 class flare. That is also a kind of circular-cum-parallel flare ribbon, but here we have a slightly different phenomenon. So let's discuss about this flare ribbon. So the database that we have used is from the SDO-AIA, which is a spacecraft or onboard, which is an instrument on board Solar Dynamics Observatory. And then we have used Goose spacecraft. The third is the RASI instrument. And the fourth is HMI instrument, which is on board Solar Dynamics Observatory. HMI is used for the magnetic field observation of that localization where the flare occurs. So this is the reason where our flare occurs on you can see this is a selected view of the sun surface. And this is the NOAA active region 112242 where the flare occurs. So nearby that active region, we have a long filament channel. Filaments are basically the cool materials, and they're supported by the magnetic flux rope inside the sun, in the sun. Okay, so and this is the structure. If you compare this observational image, the EUV image, with the magnetogram of the same region, okay. So here in the right side, you can see the magnetogram, which is called the magnetogram of the sun. So you can see where we have active region NOAA AR12242. In that region, what should be the magnetic field? It is like this. In the center, we have a positive polarity, which is shown by the plus symbol, and it is indicated by this ellipse, green ellipse. And then we have the surrounded negative polarity. It is surrounded by the overall negative polarity. Okay, and then we have also PIL, elongated S-shaped PIL, which is shown by the red box. It is inverted S. You can see the PIL, polarity inversion line, is the line between the positive and negative polarity. You can see the upper side we have positive and bottom side we have negative. So we have a positive and negative polarity inversion line. Or there is a filament channel which is in between this far away positive polarity and this the main active region polarities. You can see, compare the filament here and here. It should be somewhere here in between these yellow and the white circles. And the far away positive side is shown here, which is somewhere here on the right side of this filament. So overall configuration, photospheric configuration is something like this. We have a compact central positive polarity surrounded by the negative polarity, and we have a far away positive polarity. So if we'll draw the using some techniques that is called non-linear force field technique, if we'll use that technique to find out what the coronal magnetic field structure over there on the sun, then it will look like this. This is the same picture that I've explained you before, and these B, C, and D panels are the extrapolated magnetic field lines. We have some theoretical models for that, which used to generate some magnetic field lines, and it came out like this way. You can see the yellow lines are the yellow small lines in the B, C, and D are the innermost closed field lines. And you can also see a dome-like structure, and then some field lines is going away and connecting the far away positive polarity. So this kind of structure I also discussed in my introduction slide, that is called the faint dome structure. And if you closely look, there is a blue color spot is indicated at the center, just over the positive polarity at the center. That is the null point. That is the probable location of the null point. In the panel D, you can clearly show that is a null point. And our flux rope is somewhere here inside this magnetic dome structure. So these are the left side in the panel D. If you say this is left side is the dome structure, and the right side is called the outer spine structure, which is connecting to the far away positive polarity. So that kind of magnetic configuration is there. So if you have a dome kind of structure, okay, so the most probability is after reconnection at the magnetic null, there is a possibility of the formation of circular ribbon. Okay, right. So we found this kind of magnetic configuration using our non-linear force-free analysis techniques, right? Because we don't have direct measurement of the coronal magnetic field lines at this moment. So we have to rely on the theoretical models. So fine. So in that way, it is like this. In the flux profile, if you'll see in the x-axis, this is the flux, magnetic flux of this whole sun during the occurrence of our event. Our event started from around 3 UT and it ends up around 7 UT. So you can see the several curves are there. In the top A panel, you can see the goose X-ray flux at 0.5 to 4 angstrom and the 1 to 8 angstrom, the different colors. And the different colors profiles are the RASI X-ray profiles in 3 to 6, 6 to 12, 12 to 25, and 25 to 50 keV energy bands. So we combined the X-ray flux from GOOS as well as from the RASI. These are the two different spacecraft, and they observed the same location on the time of the flare. This is the intensity profile, which is we observed and we estimated these intensity profile from the observations, from the images. We took the images and then calculated the total counts, which gives us the flux at different wavelength, 94, 131, 304, and 1600 angstrom. And then these are plotted. So these are quite matching with the X-ray flux. You can see like this. Fine. Okay, so we have different 3 phases we have observed for this event. So initially what will happen, if you'll see in this figure ABCD, you can see the SDO AIA 131 angstrom images in the panel A. The contours are the RASI contours of 3 to 6 and 12 to 6 to 12 kilo-electron volt contours, okay, of the RASI contours. These are the X-ray contours. So when in the pre-flare phase, we have some reconnection inside the faint dome, and that is after reconnection, we have the formation of flux rope and the circular-cum-parallel flare ribbon. Okay, so we have the formation of flux rope. So you can see the dark structures like this way. These are the expanding loop system we are representing. These are the part of the formed flux rope. And in the panel C, if you'll see like this way, so these are the expanding loop system, which are nothing but the observational signature of the formed flux rope. So in the initial stage, we have the formation of flux rope inside the whole fan dome. Here the field lines are drawn over the observational image just to show you that where our dome is exists. The field line started from the outer part of this dome. You can also see some impression of the outer circular brightening, which we are called the circular ribbon here at the time of 4-5 UT. In the closed region, we can see some magnetic field structures like this way. We have some field lines which are potential, which are just the bipolar nature, and some are very shared field lines, which are not like a simple magnetic field, but they have some twists and turns. In the observation, we can also compare the field panel E and F, so we can see some of the dark thread-like structures, and these dark thread-like structures are the shared field line, which we also observe from our non-linear force-free field extrapolation techniques. So that will we can mimic the observations, the field line, what kind of field line configuration will be there. So initial stage, we found that there is a formation of flux rope inside the fan dome. Okay, inside the fan dome. Okay. So in the second case, if we'll go in the second stage, here we have some movies. If I'll run this movie one by one, so that will give you the hint that how it will form. You can see there is a brightness, and then there is some bright structure is there. Okay, and then we have some formation of bright circular-like structures. Some magnetic changes you can also see in the SDO HMI movie in here in the initial stages, and how it moving. Some moving magnetic features are here and things like this. So this is the stage phase 1. Now, if we'll go in the phase 2, in that case, we observed the field line restructuring and the eruption. So first, in the left side, B and C panel is showing the eruption of field lines from the outermost field lines. The red dotted curve structure is showing the topmost part of the erupting field line. In the second phase, we have observed some eruption from these field line, which is the outermost field line, and it is moving like this way. So their speed is coming out to be 1215 kilometer per second. And at the same time, we have also seen some brightness on the far remote region in the SDO T3 and then 4 angstrom. You can see the formation of circular ribbon appears at this time, as well as the formation of remote brightening. But at that time, we can't see a signature of parallel ribbon. So it means that the circular ribbon start to form first compared to the parallel ribbon. So that is the different case study. Then if we compare our previous 2 works that we have published in 2015 and 17, there we found that the parallel ribbon started to form first. So here it's the reverse case. So in the third case, we have found another eruption. It's like this. So this is the phase 2. If you represent the schematic representation are here, we can see the red lines, which is the outer dome lines, blue lines, which are the inner field line, and we have a flux rope, which are representing by the black field line here in the schematic. And when this field line is going to start to erupt, so there is a reconnection at the magnetic null point. So reconnection occurs between the inner blue lines and the outer red lines at the magnetic null, which is showing here in the here in this box, in this schematic. And here I have plotted some of the figures just to compare our observation with the schematic and the observation with the schematic. Now there is a phase 3 also. So interestingly, later on, after a few minutes later, we have found another eruption from the innermost part of the fan. You can see the blue, the green dotted structure, which is we have observed at the leading edge of the erupting structure, and it is going somewhere here. If we have tracked these structures and draw a height time plot, then we have found that it's going like this way, and after the linear fit, we can estimate its speed. The speed of the second eruption coming out to be 390 kilometer per second. In the right side panel, if you'll see the blue contours and the green contours. Blue are the negative polarity regions, and the green ones are the positive polarity regions. At the same time, when we have this third eruption, basically the second eruption, so at that time we notice the formation of parallel ribbon. You can see the parallel ribbon here and here. But the circular ribbon is already developed at that time. And it intensified with this eruption. So basically what we are saying, the flux rope eruption and the CME initiation. So in that case, the flux rope which is initially formed in the stage first is going to erupt now, and they are giving the parallel ribbons as well as the remote ribbons, okay, far away. Okay, fine. In this way, if you compare our the flux rope eruption with the CME schematic, it will be somewhere like this. The flux rope is going to expand, it interacts with the null point, and we have the parallel ribbon now develops along with the circular ribbon, which gets intensified. And here we have at this region where we have a flare, we have also some X-ray contours, which is which is in all the energy range from starting from 10 goes up to 50 keV, right? So means this is the indication of the flare reconnection is happening at this region where we have a parallel flare ribbon. Fine. So I would like to show you some animation which is showing the two different eruption at two different times. So if you click here in the movie, this is first and this is the second. I will show you again one and then second. There's a quick succession. You can see the two different eruptions corresponding to the two different stages of magnetic reconnection. There is a CME is also associated with this. These are some of the pictures that I'm going to show. So we can see the two arrows are representing the two different leading edges. These two leading edges we suggest that associated with the two different eruptions that we observe in the from the sun. And later on we can see the two structure merges and they combine together and they are now moving together. So the speed of the CME is coming out to be 587 km per second. Two different distinct yet connected leading edges have been observed. The circular and parallel ribbon dynamics. This is important. Which kind of ribbons form first, either parallel or the circular ribbon? So there are some of the pictures that will show how the circular and parallel ribbons are observed in the SDO AIA 304 and SDO AIA 1600 angstrom images. Here is like this. In the next case, we can see the intensity profile of the circular ribbon, parallel ribbon, and the remote region. They are the three boxes. Okay, so if you compare their intensity profile, so we can see the circular ribbon the intensity of the circular ribbon is started to increase first, then, and the parallel ribbon is started at later on at about 450. You can see that the curve is slightly enhanced later on. And the remote region is also started to build up at 345, like this way. So circular ribbon and the remote brightening ribbons, they form starting first, and this parallel ribbon, which are the innermost part, they starting to form later on according to our intensity profile. So it means so here we have a movie. I can show you the movie of you can compare how the different kind of ribbons is forms. So clearly we can see the formation of circular ribbon pattern first, and then we have the parallel ribbons formation later on in these stages. Okay. So now how we will explain these things. Here some of the nonlinear force-free extrapolation images as well. You can see the green field lines are the dome field lines, and we have some decay index measurement is also there. So decay index formula is calculated by d log bx upon log h, and bx is the potential external field, h is the height. And here is in the panel C, we can plot the height versus length. And here is the reason this line is 1.5, where the decay index is 1.5. And this is the reason also where we have a decay index 1.5. Actually, decay index is the measure of instability of the flux rope. So what we believe that if the flux rope reaches at this height where the decay index is 1.5, so it can destabilize and it can erupt. Okay, so that is the instability parameter. So we found that inside the faint dome, we have one of the reasons where the decay index is 1.5, which initiate or facilitate the eruption of the innermost flux loop. Now, at the summary, we can see the first, we have found the typical fine spine magnetic configuration. Second, the event can be described in the following 3 stages. The first stage is the we found the evidence for the formation and slow expansion of the flux loop. This is our stage 1. Okay, and we have several magnetic observational evidence we have. And the flux loop remain confined in the magnetic null point topology during the pre-flare phase. It doesn't erupt, but it will remain confined in that region. Okay. In the second stage, we have the dynamic restructuring of the field lines below and above the magnetic null point, along with the eruptive expansion of the hot coronal field lines. So that in the second case, we have the reconnection at the null point and the restructuring of the field lines. And simultaneously, we observe the circular ribbon pattern. So what we believe is, in our analysis, we suggest that both the torus instabilities is a kind of instability which triggered the eruption, and the breakout model both contributed together for the triggering mechanism of this flux loop eruption. And then in the stage third, we have an eruptive flare. We have the eruption, the third stage, we have the eruption of flux loop, which is quite nicely matching with the classical picture of the 2-ribbon flare. And subsequently, it gives rise to a CME. So these are the different stages of flare we can explain. So this work is already published in the monthly notices of Royal Astronomical Society, and you can, for more information, you can go through this paper online and read more about this event. Okay, and so the most important thing is for the formation of 2 different ribbons. First, we have circular ribbon flare, which is due to the null point reconnection. This is occurring first. And the second, the formation of parallel ribbon later on, means we have the standard flare reconnection after the eruption of the flux loop, and we have the formation of parallel ribbon. So 2 different reconnection mechanisms are there for the formation of 2 different regions. So circular ribbon flare forms first, and the parallel ribbon forms later on. So that is our conclusion for this main conclusion for this paper. Thank you very much for your kind attention.